आज क्या आप स्क्रीन देख सकते हैं?
Yes, sir.
Okay. So class, today we are going to start with the just a minute, class. So yesterday I told you about the Leibniz rule, and today, as an application of Leibniz rule, I'm going to take up this problem. Show that we are to compute the value of this integral, class. Minus z if mod z is less than 1. तो सॉल्यूशन देखिए क्लास। पहले तो मैं इसका मतलब समझा दूं क्लास आपको। बेसिकली क्लास इसका मतलब ये है कि अगर आप ये कंसिडर करें क्लास, ये z, ये वाला z है satisfying this condition. It means class, complex plane में, in complex plane you take this unit circle centered at the origin, then it means this z is any point here. So the problem says that, and here this s is certainly, this s is a parameter, and certainly, as you can see, looking at the expression for this integral, that s is varying where s is real parameter. It is varying in between 0 and 2 pi, right? So this is just obvious. So the problem says that the value of this integral will always come out to be 2 pi irrespective of that which point you take inside this open disk. So you take inside this open circle. It means in this open disk, you take any point z, the value of this integral will remain to be the same. Is this okay, class? You can see that the value of the integral is independent of, this is independent of this z. Is this okay, class? Is this
Yes,
okay,
sir.
class?
Yes, sir.
Right. So basically, why I have highlighted this, because it may so happen that in the exam somebody may ask you a problem like this. So what will be the value of this integral? So you are to locate only that whether this given point is inside the unit disk or not. So as you can clearly see that it is inside the unit disk, right? So the value of the integral will be, is this okay, class? Is this okay, class?
Yes, sir.
So there should be no confusion. Now, to compute this integral, we first of all define, so sorry, let us define a function phi we are defining, and phi is being defined on this rectangle. Now I hope you understand the meaning of this cross this and how let us define a function like this. The value of phi at s comma t is equal to EIS divided upon EIS minus TJ. Needless to say here that uh, what is the range for S? The range for S is this, and the range for the parameter T is this, right? So we have defined it very intelligently. The T is appearing here. Now, note that so please take a note class. This Z once chosen is fixed. This Z. This Z once chosen is fixed. This is any fixed Z inside this open disk. Is this okay class? So once chosen it is fixed. Now note that the phi which we have defined is continuously differentiable with respect to the parameter t. Class, this is quite obvious because when you take its partial derivative, I am saying continuously differentiable with respect to t means that is I am saying that it means if you take partial derivative of y with respect to t, then this function, this new function comes out to be continuous. And I think there should be no problem for you to take the partial derivative of phi with respect to t. There are two parameters only, s and t, and you are taking partial derivative with respect to t, and you know the meaning of partial derivative. In this situation, z is already constant, and in this situation, you will have to treat s also as constant. So this is just obvious that phi is continuously differentiable. Is this okay, class? Is this okay, class? And
Yes, sir.
and the value of this partial derivative is coming out to be this. The value of this partial derivative is coming out to be this. So you please take it as your homework. This is very easy, class. You can do it. So let me call it number 1. Now, class, let us define a function. Let us consider the function g, which is defined on closed interval 0 to 1 into c, defined by, so g is defined like this, class. G of t is equal to 0 to 2 pi phi s comma t ds. We are defining g like this. So class, if you recall the Leibniz rule, then Leibniz rule says that if let's recall the Leibniz rule. The Leibniz rule says that, which we did yesterday, that if g is defined with the help of this kind of integral, and suppose now we are given this condition too, that this exists and is also continuous, then class, according to Leibniz, this part B of Leibniz rule, it means g dash must be equal to this. Is this okay, class?
Yes, sir.
Right? So then by part B, of Leibniz rule. We have what class? We have g dash t is equal to 0 to 2 pi del phi upon del t s comma t ds. And now class, using 1, I can say this will be nothing but equal to 0 to 2 pi, and the partial derivative was this z eis divided by e to the power is minus dz its square and ds. Is this okay, class? Let me call it number 2. Is this okay, class? In fact, class, let me tell you that to calculate the value of this given integral, let me tell you what is going to be my approach. Actually, my approach is going to be the following. My approach is going to be that I am going to show that this function g is constant. I am going to show that, class, this function g is constant. That is going to be my approach. Now let's try to understand, before I go further, let's try to understand that how this approach will work. So let me first explain to you this approach. So I'm putting a star here, and now I'm moving here. So class, suppose I have shown that g is constant, right, class? This is my approach. So suppose we have shown. Now I am you the details going in reverse that way. So suppose we have shown that g is constant. Then it means what, class? Class, you know that a function is said to be constant if it takes same value at all the points of its domain. Is it okay? Is this okay, class?
Yes.
Yes, sir.
And if it is so, then it means, using the definition of constant, then it means the value of g at 0 and the value of g at 1 will be same. In particular, I am taking 0 and 1. Though the value of g at every point of its domain will be same, but I am concerned only with the endpoints. So certainly at the endpoints also the value will be same. Is this okay, class? Is this okay, class?
Yes, sir.
But please have a look. What's the value of g at 0? Class, the value of z at 0 is 0 to 2 pi, and you put just so this will be phi s comma 0 ds. This is equal to 0 to 2 pi, and what is the value of phi at s comma 0, class? The value of phi at s comma 0 will be, can someone of you tell me?
1.
Very good, 1. Right, because if you put t is equal to 0 here, so you will be left with the same numerator and denominator. So it will be 1. So you are left with ds only. 1 into ds. Is this okay? And this is coming out to be 2 pi. Right, class?
Yes.
And class, what will be the value of g1? You can clearly see that the value of g1 will be phi s comma 1 ds, and you can see that it will be 2 pi. If you look at the definition of phi st, it will be divided by e to the power is minus z, because now the t is 1, right, class?
Yes.
Right?
Yes,
And
sir.
now using this fact, it means both of these things will become, both of these values are, it means same. And hence done. Is this okay, class?
Yes.
So this is going to be my approach to calculate this value. Now, class, to, to show that g is constant, what should we show? We should show that the value of g dash t is 0 for all t in its domain, right?
Yes, sir.
So let me write here my aim as well. So my first aim is to show that g dash t is equal to 0 for all t in closed interval 0, 1. That's why class, I have started with the derivative of g now. Is this okay, class?
Yes,
Yes,
sir.
sir.
So once I show that g dash t is 0, the explanation will be complete. Is the approach clear, class? Is the approach clear,
Yes,
class?
sir.
Okay.
Yes, sir.
So now our aim is just to show that g dash t is 0. Okay, good enough. Now, class, take a look at this. Class, if you notice, this is a function of s. Let us say fs. This is a function of s. Is this okay, class? Now, class किसी का माइक्रोफोन ऑन है, प्लीज म्यूट कीजिए, डिस्टरबेंस हो रही है. नाउ इफ f of s is equal to zi upon eis minus tz, class, then you can see that if you take its derivative with respect to s, this is nothing but, class, derivative of f, capital F, with respect to s, the ordinary derivative, certainly, because here s is the only parameter. We are taking it as a function of s. So, class, you can easily see that it will come out to be this. You have to just to differentiate capital F with respect to s. So I hope you can do it. So this is your homework. And class, if you notice, this is nothing but what? F of s. You just notice. This is nothing but f of s. You have a look at f of s. Right, class? Is this okay, class?
Yes, sir.
So
Yes, sir.
it means what, class? That is, I have shown you that capital Fs is the primitive of small fs. Is this okay, class? Is this okay, class?
Yes, sir.
So therefore, class, class, from 2 what do we have? From 2 we have, therefore, from 2 or continuing with 2, you can say, uh, I write like this, therefore continuing with 2 we have, so what was 2, class? Class 2 was g dash t is equal to integral 0 to 2 pi fs ds. Is this okay, class? Rather than writing that big expression, I have just written fs for it. Is this okay, class?
Yes, sir.
And now, because capital F is primitive for it, so what will be the value of this integral? The value of capital F at 2 pi
2
minus.
pi minus capital F की value at 0.
Very good. Using the fundamental theorem, which I told you in the previous section while explaining you the Riemann-Stieltjes integral. Right, class? I
Yes, sir.
explained it to you there. So it is this. So class, now let us see what is the value of f at 0, class. Use the formula for f. This is the formula for f. So put s is equal to 0. So can you tell me that what is the value of f at 0? So if you look at it, then the value of f at 0 is this class.
Zi Zi upon 1 minus Tz.
Very good, very good. So this is Zi upon 1 minus Tz. Now, and plus let us compute the value of f at 2 pi. So class, let's have a look. So it will be Zi and divided by e to the power 2 pi I, because now the value of s is 2 pi. Is this okay, class? And minus Tz. Is this okay?
Yes,
And
sir.
class, how much is the
Yes,
value
sir.
of how much is the value of e to the power 2 pi I?
1.
Yes, very good.
One.
Yeah, very good, very good. Because you know that e to the power I theta is a periodic function of it consists of periodic functions cos theta and sin theta. Both of them are periodic of 2 pi. So the value will be 1. You know that. Cos 2 pi plus I sin pi. So class, we are seeing that f0 and f2 pi, both of them are
Equal.
very good. So therefore, g dash t is equal to
0.
0. And this is coming for all t in closed interval 0, 1. I did not take any particular t here. It was any arbitrary t, right class?
Yes, sir.
This implies that g is constant on closed interval 0, 1. And we are done. Rest you know now. Is this okay, class?
Yes, sir.
So, I hope you liked it. Good enough. Now, class, I'm going to do a very important result, what is called as Cauchy's integral formula, which so far as the Delhi of university course is concerned, I know that it is done at the undergraduate level. But class, let me tell you that at the undergraduate level, the approach to do this formula is by using the principle of deformation of paths. But because here in our course we are to adopt a different approach, so again we will have to do its proof. So if you look in Brown and Churchill, the Cauchy integral formula, then there you will see that using the principle of deformation of paths, the proof is quite easy. Though here also the proof is quite easy, but seems to be a little lengthy. So now I am going to take Cauchy's integral formula. So what is that? And I shall be making use of this integral value, which we have just calculated, the value of this integral in this Cauchy integral formula result. So what it says. Cauchy integral formula. Class, it's a very important formula. What it says? It says let f from G to C be an analytic function. So class, here I would wish to remind you a note. And what's that note? Let me share that with you from your book. Just a minute, class. This is chapter 3 of your book, which we have already completed. I don't know whether I will be able to look at this note or not. Just a minute, class. Just give me a minute. That's a very important note. And very often the note is being used in a hidden form. Yeah, it is at page 34. Yeah, it is here, class. Please have a look at this note. If we say f is analytic on a set A and A is not open, it means either A is open, and if it is not open, we mean that f is analytic on an open set containing A. Right, class? So it means, class, this is an assumption which goes all through in this book. This is the assumption taken by author, that either the function f, if a function f is analytic, either it will be defined on an open set, and if it is not defined on an open set, then it is understood. Suppose it is defined on some A, then it is understood that f is analytic on an open set containing A. Is this okay, class? So author has taken this understanding throughout the course. Meaning thereby is that, class, here this set G is either open, and or if it is not open, then it means there is some open set which contains G, and then f is analytic on that open set. Is this okay, class?
Yes, sir.
Okay,
Yes, sir.
But okay, good enough. But for the time being, nothing to bother. So an analytic function, and suppose that
अरे यार वही तो मैं पूछ रहा हूँ क्या खाओगे वही मैं खा के आऊँ सबसे प्रॉब्लम नहीं रहती सबसे बड़ी कि क्या खा के
suppose that, class, we have a ball having center A is some complex number, of course, radius r, and we are talking of this closed ball. This bar stands for closed. It does not stand for the closure. It stands for the closed ball. And suppose we have this closed ball sitting inside G. Now if further we have this information, if we have a path or curve given by this formula, oh sorry, it is nothing but the, if you notice, it is nothing but, class, a circle centered at A and having radius r. Is this okay, class?
Yes, sir.
This is, yeah, so this is nothing but the boundary of this open ball, B, A, comma, R. And of course here, this parameter T will vary in between 0 and 2 pi. So that, so ultimately, class, you can see that trace of gamma will come out to be a circle. So it will come out to be a circle centered at A having radius r. So this is gamma, and this is trace of gamma, and I can say that every point here is of the type gamma t. Is this okay, class?
Yes, sir.
Now you are well familiar with all this. What gamma is doing actually? Gamma is taking the 2 pi. You know all this. Gamma is continuously differentiable. It is, moreover, this path is directed. You know this. Fine. So if we have this curve class. Then Cauchy integral formula says that the value of f at z, the value of f at z will be equal to 1 upon 2 pi I integral over gamma. Gamma means class the points on this circle, the points here, points on the trace of gamma. U minus z for z minus a less than r. So class, before I give you the proof for it, let me give you the interpretation for this formula. First of all, class, take a note. So before I give you the proof, let us interpret it. So I call it formula A. So I am giving you interpretation for A. That is very important, class. First of all, let us try to understand what information does this formula A provide us. So class, first of all, take a note. Any z satisfying this condition means what, class? It is the same z. So all these three z's which I have put with in black font, they are same. And any such z means, class, what? It means any such z must be here. Right, class?
Yes, sir.
Yes,
Right,
sir.
right? So first of all, take a note of this thing, that this z is inside this open ball. Secondly, class, have a look at this w, where this w will be.
In G.
This w, no, you are integrating over this curve. It means this w is on this curve, na?
Yes, sir. Yes, sir. Okay.
Okay, bhai. When you say integral, suppose x square dx, x is going from 0 to 1, then where is x? It means x is varying from 0 to 1, na? It means x is varying on this line segment, right? So now because you are taking integral over this path, it means these points are on this path, na? Right? Is this okay?
Yes, sir.
Yeah, so these points are on this path. So these w's are here actually. This is actually w. The points on this path are w. So class, now let us start interpreting this formula. I call it left hand side of this formula and I call it right hand side of this formula. Now class, this is something very basic which you know from maybe 9th class or maybe 8th class, that if you have something like this, something like A is equal to something like some expression B. So if you know B, you can determine A, and if you know A, you can determine B. Right, class? It means, class, in formula A, if you know right hand side, you can determine left hand side. And if you know left hand side, you can determine right hand side. Is this okay, class?
Yes, sir.
Okay. So keeping this into mind, let us interpret it. So class, suppose, now, so I'm going to give you two interpretations of it. First interpretation is the following. Suppose we know RHS of A. Suppose we know the right hand side of A. So class, what is the meaning of knowing the right hand side of A? The meaning of knowing the right hand side of A means, class, it means you know this, right, class?
Yes, sir.
And what does it mean? My special focus is on this very expression only. It means, class, that you know the values of f on the points of gamma. On this circle, on the boundary of this circle, w's are on the boundary of this circle, and you know the values of the function at these boundary points. Right, class? Right, class?
Yes, sir.
And now suppose, class, you don't know the value of f at z, which is a point interior to this open ball. Then using this formula, class, if we know right hand side of this, then we can determine the value of f, sorry, that is, we know the values of f at the points on the boundary of BAR, then we can obtain, which is nothing but left hand side of A, the value at any value of f at any point inside this ball. Isn't it, class? Because once you know this, once you know the value of this expression, then certainly you will get this, and which is nothing but the value of, so whatever, if, I mean, you want to determine the value of at whatever point, you use the same point here. Is this okay, class?
Yes, sir.
So don't you think that it's a very interesting phenomena, that just by knowing the values of a given function at the boundary points, this formula helps you to determine the values of the function at the points which are inside it. Once you are able to compute this integral. Is this okay, class?
Yes, sir.
Now, second interpretation. Second interpretation we get on rewriting A. We rewrite A as this. Integral now again the same way we can interpret it, class. This is, let us say, left hand side, this is right hand side, and let me call this time it as A dash. So class, again, if we know right hand side of A dash, so now class, if we know the right hand side of A dash, right hand side of A dash means, class, that we know the values of the function at the points inside the ball. Is this okay, class?
Yes, sir.
Then we can determine the value of the integral this, right, class?
Yes,
It's
sir.
okay. So it's a, let me tell you, class, Cauchy integral formula is a very powerful tool. It means it is a formula which tells you that if you have an analytic function, then if you know its values inside a circle, then you can compute this integral. And if you the integral written in a, and if you know the value of the integral, then you can compute the value of the given analytic function at any point inside the open ball. So it's a very powerful tool class, let me tell you. I don't remember if we have any such tool available in the frame of real valued functions. Okay, class. So maybe now I can start with the explanation. Or you can say proof. Now, class, to write down the proof, I will be making use of the linear structure of the complex plane. Class, you know that, I think I explained you this someday. Class, you know that by definition, what is this? By definition, this is the collection of all those Z, of course, in the complex plane, needless to say. Recall the definition of open ball from metric space theory. Collection of all those points whose distance from A is strictly less than R. Right, class? This is equal to Z in this, such that, and class, all of you know that the radius is always positive. It's never zero. So you can write it like this. Is this okay, class? Now you call this as W. And if you call this as W, class, what will be Z? Z will be RW plus A. Is this okay, class? Is this okay, class?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
RW plus A such that magnitude of W is less than 1. And class, further, this is nothing but A plus R times this set is nothing but this, class, using the linearity. And class, this is nothing but A plus R times. If you notice, class, this is nothing but unit ball centered at this thing, centered at origin and having radius 1. Is this okay, class?
Yes, sir.
Yes, sir.
What I'm trying to tell you is that any, using the linear structure of C, because Z minus A will again be in C. I have used the fact that C is closed with respect to addition. Then I have taken Z minus A into 1 upon R. So scalar multiplication I have taken. So I have used the linear structure of the complex plane. So using the linear structure of the complex plane, I have explained you that any journal ball in complex plane is nothing but the magnification of the unit ball centered at origin followed by translation. Right, class? That's why, class, whenever you are dealing with a structure on some vector space, it is just sufficient enough to make your discussion at the ball having radius 1 centered at the origin rather than having any journal ball. Is this okay, class? Is this okay, class? So,
Yes, sir.
class, in our statement, we have taken this journal ball. So now I am going to replace this ball by this one. So I am going to write, first of all, without loss of generality, we may consider this ball and the corresponding closed ball, in fact, the unit closed ball contained in G, rather than that journal ball. Is this okay, class?
Yes, sir.
So now let us fix some Z. If you wish, you can call it Z naught, such that mod Z is less than 1. It means, class, we are taking some fixed point inside this circle, which is, for example, this. So let me denote it by black. So I am taking some Z, and once chosen, it is fixed. This Z is inside this ball, if you notice. Is this okay, class?
Yes, sir.
Right? Now what we are to prove? Let us recall that. We are to show that the value of f at this z which I have taken is equal to 1 upon 2 pi I integral over gamma fw divided by w minus z. We are to show that fz is this, right class?
Yes, sir.
Or,
Yes, sir.
or let me reformulate this expression. Or we are to show that fz is equal to, now I am not denoting it by black font, 2 pi I. And class, if I use the substitution w is equal to EIS class, then this expression will become this. You can see that if you take EIS, then you will get that curve if S is in this range. You will get the ball, na class? You will get this ball. Centered 0 and radius 1. Right class? It is nothing but this ball. Right class?
Yes.
So now it will be F, and instead of W we put e to the power is, and W is e to the power is minus Z, and what will be dW? I EIS ds, right class? And S will go from 0 to 2 pi. So we have changed the integral, which was initially integral with respect to this complex variable. Now we have changed using the idea of parameterization, right class? We have used the idea of parameterization, and now we have changed it into an integral, which is in fact an integral depending upon a real parameter, right class? S is varying in between 0 to 2 pi. Is this okay?
Yes, sir.
Right? So let me call it, so far I have not started numbering. So class, let me call it number 1. Right class? Now class, as we did in the problem, while computing that integral, again I am going to follow more or less a similar kind of approach. So let us define, it's a very strong approach, let me tell you class. Let us define this phi of s comma t is equal to, sorry class, बुरा तरीका है लिखने का, you will get confused. Define phi 2 pi cross 0 to 1 into c by phi of s comma t is equal to, so now it is clear that s is coming from here and t is coming from here. And how we are defining this function class? We are defining this function f of z plus t into EIS minus z. Now class, this is really typical. This you can think of just by practicing the things. This, and let me call it class number 2. Now class, here this is important that this function which we are talking about, this point must be inside the unit ball, because then and then it will make sense. If it goes outside the unit ball, then certainly we can't talk of f on it, right class? because now we are concerned at the unit ball only. Is this okay, class?
Yes, sir.
Yes, sir.
So let me tell you, note that note that if you take its modulus, then class it will be z 1 minus t plus teis. Just simple algebra. I hope you are getting it, what I have done. I have just collected the terms containing z, and then using triangle inequality, it will be this plus uh, actually I have not taken in mod outside 1 minus t because t is less than 0, so 1 minus t will be positive, and likewise here because t is bigger than 0 it will be positive, and modulus of this. Now class, you know that modulus of e to the power is always 1, right class?
Yes, sir.
And class, we are taking the point z, so that modulus of z is less than 1. We have taken our z. If you look at the choice of our z, right class? So mod z is less than 1. So it means this combined thing is less than 1 minus t plus t, and which is nothing but 1. It means class, this element is coming out to be in our ball. It means this belongs to, sorry, it means rather than writing this, I must say that it means this is inside this ball. Is this okay, class?
Yes, sir.
So I can say why I have written this. Therefore, one makes sense. Sorry, two makes sense. Because class, we should always be sure about the well-definedness of any expression. So here, this was the only, probably this could be the only issue, that whether this combination is giving us an element inside B01 or not. But we are observing that yes, still we are inside B01, so we are safe. So we can use this kind of combination. And class, moreover, now you can trust me that this phi st is continuously differentiable, is continuously differentiable with respect to the parameter t. Because you know that f is analytic, so it means f is differentiable at this element. So we can talk of the continuous differentiability of phi with respect to t. I will be writing this, don't worry. Moreover, this is continuously with respect to this, and the derivative of phi with respect to t, this is coming out. If you allow me, let me call it phi naught. Okay, leave it. So class, you can see that this is coming out to be EIS divided by EIS, this f dash, this. So first we differentiate f, and then we take the derivative of its angle with respect to t. Is this okay, class? This is how we do differentiation with respect to a real parameter. T is a real parameter, na class? Is this okay, class? So this cancels this, and ultimately we are left with equal to EIS f dash z plus t EIS minus z. We are left with this. So class, let me call it number 3. Okay. And class, if you allow me, let me call this as some function psi, a function of parameter s. So let me consider this expression as function of s. Okay, good enough, class. So class, now consider, now it will not take me more than 5 minutes. Now consider this function g defined on closed interval 2 pi into c, uh, and this is how this function is defined: 0 to 2 pi pi s comma t ds. And class, let me tell you what is going to be my approach. Now class, my approach is going to be again that I will show, we will show that g is constant. And we will be done. See class how. Suppose class, once we have shown that g is constant, right? Suppose once we have shown that g is constant, so suppose, so now I am explaining you the approach. Now suppose we have shown that g is constant, then it means what, class? Then it means the value of g at every point of closed interval 0 to 2 pi will be same, right class?
Yes, sir.
Yes, sir.
In particular, the value of g at the endpoints will be same.
Yes, sir.
Is this okay? Now, let's have a look at the values of g at 0 and values of g at 2 pi. Now, what is gt? Gt is 0 to 2 pi. And what is gt? 0 to 2 pi and phi st. And you put the value of phi st. So class, value of phi st is what? The value of, this is how we have defined phi, right class?
Yes, sir.
So let us put this. So let us put phi. So it is this. Minus fz. This is how we defined phi of s comma t, and this is ts. So class, compute the value of g at 1, or you can compute now. Therefore g at 0 will be what, class? Put t is equal to 0. It will be 0 to 2 pi e to the power is f. You will be left only with z when you take t is equal to 0, right class?
Yes, sir.
Divided by e to the power is minus z ds minus 0 to 2 pi fz ds. I think you must have got it. I have separated this portion. Is this okay, class?
Yes, sir.
So this is quite simple. And class, what is this? Class, if you notice, this is independent of s. This is independent of s. It is depending upon z. So you can take it outside the integral sign. 0 to 2 pi e to the power is divided by e to the power is minus z ds minus fz into, and the remaining will be class 2 pi integral 0 to 2 pi ds. Is this okay, class?
Yes, sir.
Yes, sir.
And class, what is the value of this
Yes,
integral?
sir.
What is the value of this integral?
2 pi.
2 pi, very good. So ultimately you get 0. So value of g at 0 is 0. Now let us compute the value of g at 1 also. The value of g at 1 will be what, class? For t you put 1 only. Here for t you put 1. So if you put 1, class, you can see that this minus z will cancel this z, right, class?
Yes, sir.
Right, class?
Yes, yes.
So what will be g1, class? You can see that g1 will be 0 to 2 pi EIS f operating on EIS, because now z cancels. Once you take t is equal to 1, divided by EIS minus z minus fz ds. So class, we know that g0 and g the value of, sorry, what is this, class? Oh, sorry, class, take a note. You have committed a mistake. No one of you pointed it out. It is the class, the variable, yeah, the the variable s is varying in 0 to 2 pi, class. This is the variable s varying in between 0 to 2 pi. Class, the variable g is varying in between 0 to 1. Sorry, rest is okay. Otherwise, oh, and when I am writing here 2 pi, just because of that, that is a mistake. Though I am calculating g1, because that is already there in my mind, right? Is this okay? So that was the only mistake, sorry. By chance I wrote 2 pi there. So class, now this value and this value, both of them must be equal in view of this, right, class?
Yes, sir.
Yes, sir.
So therefore g1, which is nothing but 0 to 2 pi EIS FEIS divided by EIS minus Z minus FZ ds. It means this must be equal to the value of g at 0, that is 0. Is this okay, class?
0.
So we have used the fact that g1 is equal to g0. We have used this fact since we have this. And now, class, it's simple. You separate these two, 0 to 2 pi EIS F EIS upon EIS minus Z ds is equal to integral 0 to pi fz ds. Is this okay, class? And this is equal to fz will be taken out, and then rest of the value of the rest of the integral will be this. Is this okay, class? Is this okay, class?
Yes, sir.
Yes, sir.
So therefore, what will be, class, fz? Therefore fz will be 1 upon 2 pi I 0 to 2 pi EIS FEIS divided by e to the power is minus z ds. Class, I multiply I here and I multiply I here, right, class?
Yes, sir.
Right, class?
Yes, sir.
Class, now you can see that taking back that substitution, W is equal to EIS, you can see that this is nothing but
W minus Z
yeah,
dW.
sorry, yes, W minus Z dW, right?
Yes, sir.
And you get the formula. So I
Yes,
have
sir.
just, so far what I have done, so far I have just explained you the approach. So my approach is going to be to show that G is constant. And to show that G is constant, what will be my approach? To show that the derivative of G On closed interval 0, 1 is
0.
0.
0.
Right? So class, it will not take me more than 5 minutes. Please take a note. Because phi is continuously differentiable, so using the B part of Leibniz rule, we can talk of the derivative of G and what will be G dash T class. है ना? So now, using part B, if you remember, I used the same part in that problem as well. Part B of Leibniz rule, we have class, what will be G dash T? G dash T will be class G dash T is equal to 0 to 2 pi del phi by del T S comma T ds. Is this okay, class?
Yes, sir.
Right? So class, I think we should stop over here, and this I will be taking tomorrow to show that G dash T is 0, and finally that will complete the details, because once we have shown that G dash T is 0, it means G is constant, and rest of I have already explained to you. Is this okay, class?
Yes, sir.
So let's stop over here.
Thank you, sir.
Yeah, just wait for a minute. I'm taking your attendance. Yeah, Bhavana, Bhavesh, you want to say something? Bhavesh, Muskan? Bhavesh, Muskan, you want to say something?
No, sir.
So both of you guys have raised up your hands?
Sir, I'm trying. It's not being raised down.
Okay. And Bhavesh, you? Okay. Just a minute, class. Let me take your attendance. Okay, class. Thank you very much. I have taken your attendance. We will connect tomorrow. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you,
Thank you,
sir.
sir.
Yes, sir.
Okay, all of you take care.